Hello everyone. I'm finally doing the CNCM online round 3 problem 3 that has been delayed for quite a while, but I've finally gotten to it. And let's look at it. My name is Eli Park and I've written this problem. So let's first read the problem statement. So it says, this was the third problem on our CNCM online round 3, and it says, let a of 1 equal 1 and a of n plus 1 equal a of n times p of n for n greater than or equal to 1, where p of n is the nth prime number starting with p of 1 equals 2. Let tau of x be equal to the number of divisors of x. Find the remainder of this sum, and when that is divided by 91 for positive integers d. Recall that d bar a sub n denotes that d divides a of n. So how we're going to tackle this problem is that we're going to first look at this inner sum first. We're going to realize that there's going to be a closed form of that inner sum with in one variable, which is n. And then once we get that, we can evaluate the whole sum. So let's take a look at this first. We see that we're investigating each d that divides a sub n, and then we have a divisor, the number of divisors function. So just for the sake of this, we first realize that a of n, for all a of n, is going to be equal to the product of individual primes. So what I mean by that is that, for example, a of 4 is going to equal 2 times 3 times 5, and then a of 5 is going to equal, say, 2 times 3 times 5 times 7. And we see that it's just a product of individual prime numbers, and that there's no overlap. So for example, we're not going to have something like 11 squared or something like that. We're not going to have this exponent up here. That's the first thing we want to take note. So now we want to consider some smaller cases just for the sake of investigation. So just for the sake of an exercise, let's first find tau of 30. We want to find a number of divisors. So how we do this, at first we know that 30 is equal to 2 times 3 times 5. And then we're going to split this up, and then we know that the smallest number of prime factors that a divisor of 30 could have is 0. And then the largest is going to be 3. So starting with 0, there's only one factor of 30 that has 0 prime factors, which is just 1. And then there's 3 prime factors of 30 that have 1 prime factor. Sorry, there's 3 factors of 30 that have 1 prime factor, which is 2, 3, and 5. And then I'll rewrite that 5. And then for this, and then we just keep going, and we realize that next we have 6, 10, and 15. And lastly, we have just 30. What we realize here is that we should have 1 here, 3 here, 3 here, and 1 here, which gives a sum of 8. And you should realize that this is Pascal's triangle. This is not a surprise, guys. As we realize that this is, think about it here, if we are selecting 3 prime numbers from this, from 3 selections, this is just going to be 3 choose 3. And then if we're selecting 2 prime factors from a set of 3 primes, we have 3 choose 2 options. And then similarly, we have 3 choose 1 option and 3 choose 0 option. So this being said, we now know that a number of the form this, where we have, or similar to that, where we have no prime number with large exponents, is just going to be 2 to the x, where x is just, actually I won't use x because it's been used. I'll say 2 to the y, where y is the number of prime factors. With that being said now, we can start moving on. We now run a similar process on the actual a of n. I'll write a of n plus 1 for this sake. So we can split this up, and because we're considering each d for d divided a of n. We consider the ones with the d's with n prime factors. We first consider the ones with n prime factors. and then we can consider the n minus 1, and then we can do dot 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 all the way down to 1 and then to 0. We notice that for the n, if there's n prime factors in D, then we realize that there's only one possible D that could be such, which is when just D is equal to a sub n plus 1. And then we also, there's only one possible option, but then we realize that that one possible option gives a tau of D of 2 to the n from our earlier result. And then going down similarly, we find the D's that have n minus 1 prime factors. We realize that there's going to be n choose n minus 1 such options, and each of those options are going to yield a tau of D of 2 to n minus 1. And then going down, we can keep filling this out, and then we eventually reach n choose 1 times 2 to the 1, and n choose 0 times 2 to the 0. Now, we see that this is something that we can write, and then into a summation form. We can rewrite this into saying from n equals, sorry, I won't write n, from y is equal to 0 to n, this is just a sum from y equals 0 to n of n choose y times 2 to the power of y. But by the binomial theorem, you can research this if you're not very familiar to this, this is going to be equal to 1 plus 2 to the power of n, which is just 3 to the n. So hence, what we just figured out is that considering an an plus 1, we're going to get 3 to the n. So clearing all this stuff out of the way, this gives us that we can rewrite our sum from n equals 1 to 2020, but this inside part, for each n, this inside part is just 3 to the n minus 1. Because remember that a of n plus 1 yields 3 to the n, meaning a of n is going to yield 3 to the n minus 1. So now we just have a finite geometric series on our hands. So we will just write this out. We just have 3 to the 2019 plus 3 to the 2018 plus all the way down to 3 to the 0. I'll continue this on the next slide. This just becomes 3 to the 20 over, sorry, I didn't mean to write that. This becomes, writing this as a difference of two infinite geometric series, we're going to get 3 to the 2019 over 1 minus 1/3 minus 3 to the negative 1 over 1 minus 1/3, which is going to give us 3 to the 2020 minus 1 all over 2. So this is going to be our answer. But remember, looking back, we know that we want to take this mod 91. And we're finding the remainder when this is divided by 91. So we want to take this, taking 3 to the 2020 minus 1 over all over 2 mod 91. We'll just find what this is, mod 91 first, and then we can remember to, we'll put a star right here, to remember that we don't, to remember to divide by 2 at the end. So 3 to the 2020 minus 1 mod 91. By Euler's theorem, we can say that this is congruent to 3 to the 2020 mod phi of 91 minus 1. But phi of 91 is equal to 91 times 6 over 7 times 12 over 13, which is going to give us 72. So we just need to take 2020 mod 72 to greatly simplify our exponent. So taking 2020 mod 72, we can do 2020 minus 2160, as this is a multiple of 72. This gives us minus 140 40, and then plus 104, which preserves mod 72, gives us 4. So what this tells us is that 2020 mod 72 is just going to be equal to 4. So 3 to the 4 minus 1 is just equal to 80, but we have to not forget to divide by 2 at the end, and we note that 80 mod 91 all over 2, since 80 is already divisible by 2, this is going to give us our grand answer of 40. And thank you for watching this video. Look out for some more YouTube videos. We're going to be posting our CNCM countdown tournament primetime videos on our YouTube. And I hope you look forward to the tournament and those videos. Thank you.